All right, I want to talk to you about these exponential functions, or these sorry, not exponential, rational functions. And I'm going to use this one problem to kind of talk about everything all at once, or at least attempt to. And I'll do it as quickly as I can. So I'm going to talk a little bit fast. You can always put it at half speed for YouTube and listen to me talk really slow. A rational function is going to look like this when you graph it. It's got something called an asymptote. You have to say that quickly so it doesn't sound like you're swearing. So it's an asymptote with a P. And this vertical line here is the vertical asymptote. And the horizontal line here is the horizontal asymptote. So looking at a graph, a rational function, the most basic rational function, which we would call a parent function, is 1 over x. And there it is. We can see it's got a vertical asymptote here and a horizontal asymptote here. What creates that asymptote, that vertical line, is that the one number you can never, ever divide by is 0. If you divide by 0, black holes happen, algebra explodes, bad things. So 1 divided by 0 is a problem. It's undefined. And as you zoom in on x, as x gets super duper small, 1 divided by 0.1 is a big number. 1 divided by 0.000001 is an even bigger number. And so you're going to keep dividing by these smaller and smaller decimals, and you're going to keep getting bigger and bigger numbers, which is why this graphed line explodes off towards infinity, but never quite gets to 0, because if x is 0, that's a problem. So it never quite gets to 0 here. As x gets to be negative 0.000001, we get super big negative numbers, negative infinity, and it explodes down here. So that's where that asymptote is coming from. The horizontal asymptote, the back and forth one, is saying as x goes towards infinity, as x gets really big, 1 over 4 is 1/4. That's a pretty small number. 1 over, here we go. Yeah, 1 over 10 is 1/10. Here we go. 1 over 10 is 1/10. Small number, and we can keep going, and so on and so on and so on. It's going to get smaller and smaller fraction or decimals, but never quite 0. You can divide 1 by a bajillion, it'll still be a number, it won't be 0. And so or it'll still be a decimal, it won't be 0. So as x goes towards infinity, this horizontal asymptote, this horizontal line gets closer and closer to 0, but never quite gets there. Same thing going the other direction. It'll never quite get to 0 going towards negative infinity, but it'll get super duper close. So these asymptotes are super duper close, but never quite getting there. All right. One of the questions asked about domain and range. My hand is like flying around here. You just can't see it because I'm just my voice. One of the questions asked about domain and range. Domain are all the input values. So we would say that x could be anything except 0. That's the one number that's not in the domain because you can't divide by 0. But x could be anything else. So the non-mathematical way of saying it is everything except 0 is the domain. For the y, in this case, it'd be the same thing. All the outputs, all the numbers that we could possibly get, 4, 2, 1, 1/2, 1/4, all possible except 0. We'll never quite get down here to 0 on the y-axis. So the range is the y's, it's all the outputs. It could be everything except 0. That's domain and range. We can move this around. I could put -2 here. You'll see that the graph shifted. It moved 2 to the right. And the reason it moved to the right 2, even though I put -2 here, is because the one number you can never divide by is 0. And 2 minus 2 is 0. So if x was 2, that'd be a problem. 2 minus 2 is 0, and you can't divide by 0. So every number in the domain, all the x values work except for 2, because 2 minus 2 is 0. I put, I don't know, x plus 4, x plus 5. I clicked the wrong button. That's right, x plus 5. Again, the graph shifts so that this vertical asymptote is at -5 because -5 plus 5 is 0. That's a problem. You can't divide by 0. So you can see that the denominator, that's what causes this vertical asymptote. That's what tells us that our domain is everything except -5, because -5 plus 5 is 0. So if it's asking you, and I don't know where it is, here we go. If it's asking you, where is it? Sure, here. What's going to give you the correct vertical asymptote? Well, the vertical asymptote is asking, what's going to make the denominator 0? What's going to make that bottom number 0? And that's where that vertical asymptote is going to be. That's the problem. That's what we have to avoid. Looking at this one, there is a vertical asymptote, and it's at -3, which means that I'm going to have a plus 3 on the bottom. Oops, try that again. Plus 3 on the bottom. That's going to give me a -3 issue. If x was -3, -3 plus 3 would be 0. So I've created that vertical asymptote at -3, which is exactly what I'm supposed to have in this problem, -3. I have not talked about the horizontal asymptote yet. To move the graph up and down, I can just put, I don't know, +1. Now that vertical or the horizontal asymptote is here at 1, because I'm just shifting it up and down. I could do -5. And you can see it's shifted to -5 here. In the problem that you have, it looks like that horizontal asymptote is at -2. So I'm going to put minus. That's it. That's the equation. So for number 3, I needed to have a vertical asymptote at -3. The vertical asymptote is asking what will make this go to 0 in the bottom. That's a problem. And the up and down, the vertical or the horizontal asymptote, moving the graph up and down. The horizontal asymptote needed to be at -2, so I can just put -2. There you have it. There's my horizontal asymptote. Because this is getting to be a long video already, I think I'm at, oh no, I'm only at 7 minutes. I'm going to do one more thing in this video, and then we can just call it good in there. There's one more set of rules that I'm going to write down. The basic rule for vertical asymptote. There we go. It's scribbled so it doesn't, it's whatever. Vertical asymptote is really, we only care what's on the bottom. We want to know what's going to make that denominator 0. That's it. So even if you had something like, I don't know, 9x squared minus 16 in the denominator, doesn't matter what's on top, because it's only the bottom that gives us a problem. You may have to factor this, because if we want to know what's going to make that equal 0, if there's a squared in there, well, you're going to have to do a little bit more work. So that can be factored to 3x times 3x is 9x squared. 4 times 4 is 16. Now, I haven't looked ahead yet to know if that's the style, the difference of perfect squares, if that's the type of question they're going to ask. But I know there's at least one problem that asks about squared, which means you're going to have to factor. So the only thing that could make this 0 would be if I had 4/3. 3 times 4/3 plus or minus 4 would give me 0. And I just solved that in my head. Oops. Minus 4 equals 0, but you could write it out. You do the same thing here. This would be negative 4/3. So you may have to factor, you may have to solve to figure that out. It might be as easy as x plus 3, which means it's just -3. Vertical asymptote, done. Horizontal. If it's 1 over something, whatever's being added to the end, plus 3, that's the horizontal asymptote. If it's 1 over something minus 2, that's the horizontal asymptote. If there's nothing there, that maybe, and there's nothing at the end here, we can always add 0. You can always do plus 0, it doesn't change anything. So the y, or the horizontal asymptote would be y equals 0. And keep it going. This is a lot of stuff at once that I'm throwing at you, but it's the whole, it's like almost the entire unit quickly. Or maybe 3 lessons. Either way, it's a lot coming at you at once. Okay, what happens if it's not 1 over? So it could be that you have, I don't know, something like x squared plus 2x plus 4 over, I don't know, x cubed minus x. Okay, that could be a rational expression. If it's got a polynomial on top, so you've got a big thing of stuff on the top, not just 1, then we don't care about most of it. All we're concerned about is these leading powers here. If the first power is smaller than the second power, the first power is smaller than the second power, it's always going to be y equals 0. That's the horizontal asymptote. That's where that horizontal line is. If they are the same, so I'm looking at y equals, I don't know, 7x squared plus something, doesn't matter, divided by 3x squared minus something. Doesn't matter what this stuff is. I only care about the leading power here. If they're the same, and you want to know where that horizontal asymptote is going to be, we're going to look at the leading coefficients. It's going to be y equals 7/3. So whatever these first numbers are, that's it. That's the answer, if these are the same exponents. Smaller on top, bigger on the bottom, always y equals 0. Doesn't matter what these numbers are. If they're exactly the same exponents, we look at the leading coefficients. That's it. That's the answer. If the top is bigger, so I don't know, 8x to the 5th minus 4 over, I don't know, 2x to the 3rd minus 12, whatever. Again, we don't care about this stuff. If it's bigger, there isn't going to be a horizontal asymptote. And we could show that. I could pull up another graph. I'm not going to. That's it. That's how you decide. That should help you with most of these problems. Let me know if you have other questions.